The trembling started as Professor Leo Brantz reached for the copper cylinder resting in its protective case. February 3, 1943. Telefunken Research Laboratories, Berlin Tempelhof. His hands weren't quite steady as he lifted the device, no larger than a coffee mug, weighing barely 3 kilograms, and turned it slowly in the laboratory light. What he held contradicted everything his nation's finest physicists had calculated about microwave radar. This cannot be generating such power at 3 gigahertz, he thought. Our mathematics proved such power levels were impossible at these wavelengths. 24 hours earlier, a Luftwaffe night fighter had torn a Royal Air Force Sterling bomber from the sky near Rotterdam. The aircraft belonged to Pathfinder Force, carrying secrets so tightly guarded that it included self-destruct charges designed to vaporize the technology before enemy hands could touch it. Those charges had failed. German recovery teams discovered the radar system in a state of partial preservation. The copper magnetron was still warm from operation when they pulled it from the wreckage. What they found inside that damaged fuselage would force a reckoning. Germany wasn't just behind in this technological race. They were operating in an entirely different realm of physics, years behind in understanding how to unlock the power of centimetric wavelengths. This catastrophic gap hadn't come from any single failure. It had been born from a decision made during Germany's moment of greatest triumph. Following France's spectacular collapse in June 1940, when Britain seemed isolated and vulnerable, Hitler issued a decree that would cripple German scientific ambition for the entire war. The Führer decreed that no research project could receive priority funding unless it promised definitive military results within approximately 2 years. Swift victory made long-term thinking seem wasteful. That single administrative decision, rooted in overconfidence and the intoxication of conquest, killed the very research that might have given Germany its technological edge. While British scientists were achieving breakthroughs that would revolutionize warfare, German radar development withered. Wilhelm Runge, head of radar development at Telefunken, had watched the mathematical limitations become official policy. The theoretical foundation existed. German scientists understood the principles behind cavity magnetrons. Hans Hollmann had even filed a patent for a multi-cavity design on November 27, 1930, years before British work. His United States patent, 2,123,628, granted July 12, 1938, described a magnetron with multiple segments connected by straps to increase efficiency. Soviet physicists Nikolai Alexeyev and Dmitry Malirov had published research on cavity magnetrons in Leningrad back in 1936, work that German scientists had reviewed and discussed in their journals. The theory was never secret. International physics journals had carried articles on magnetron development throughout the early 1930s. What escaped German engineers was the practical achievement at high power levels and stable frequencies. Calculations performed by some of the Reich's most capable physicists suggested that magnetrons operating above 1 gigahertz would become fundamentally unstable, prone to frequency drift that would render them useless for precision radar. Experimental prototypes built in German laboratories had seemed to confirm these fears. The devices either refused to oscillate at desired frequencies or produced such minimal power, perhaps 30 to 50 watts, that they appeared impractical for military purposes. Faced with these calculations and experimental failures, reinforced by the urgency of wartime production, German radar development committed entirely to lower frequencies where established technology functioned with reliability. By 1942, German radar systems operated primarily between 90 and 600 MHz, using robust triode tubes and specialized vacuum tubes that German industry could manufacture consistently. These systems worked admirably for their purpose. The technology was mature, understood, producible at scale, but they required antenna arrays measured in meters and provided resolution measured in hundreds of meters. For early warning and general aircraft tracking, these limitations proved acceptable. For precision applications, they represented constraints that German engineers believed were unavoidable given the laws of physics as they understood them. The Würzburg radar represented the pinnacle of German tracking technology. Operating at 53-centimeter wavelength with a 3-meter parabolic dish antenna, it could track aircraft with acceptable accuracy at 40 kilometers range. The system used a conical scanning technique, employing an offset receiver feed that rotated at 25 Hz, providing angular resolution of approximately 0.2 degrees in azimuth and 0.3 degrees in elevation, sufficient for directing night fighters toward bomber formations, but not precise enough for direct gun laying without optical assistance. The larger Würzburg Riese, Germany's most advanced operational radar, featured a much larger 7.4-meter parabolic antenna and a more powerful transmitter. This extended maximum range to 70 kilometers against aircraft targets, with improved accuracy needed for direct gun laying. The system was too large for mobile deployment, typically mounted on railway flat cars as the Würzburg Riese E variant. Approximately 1,500 of these systems were produced during the war, forming the backbone of German air defense. Freya early warning radars, operating at wavelengths between 2.5 and 2.3 meters, provided long-range detection capabilities that complemented Würzburg's precision tracking. With peak power output of 15 to 20 kilowatts and pulse repetition frequency of 500 Hz, Freya could detect approaching bomber formations at ranges up to 160 kilometers. The system couldn't accurately determine altitude, but it provided early warning that allowed Würzburg stations to be alerted and night fighters to be scrambled. Together, these systems formed the defensive network that had inflicted substantial losses on RAF Bomber Command throughout 1941 and 1942. German confidence in their radar superiority wasn't without foundation. Germany had deployed radar earlier and more extensively than any military except the British. German radar-directed anti-aircraft fire was more effective than anything the Allies could match in 1941 and early 1942. The night fighter defense system, using ground-controlled interception guided by Würzburg radar, had achieved remarkable success rates. German engineers examined their radar network with justified pride. They had built effective, reliable systems using sound engineering principles. What they didn't know was that British scientists had transcended the limitations German theory declared absolute. That confidence began eroding in late 1942. RAF Bomber Command losses, which had been climbing steadily as German night fighter tactics improved and radar coverage expanded, suddenly began diverging in ways that troubled German air defense analysts. British bombers seemed able to navigate with precision through heavy cloud cover and darkness. They found targets in conditions that should have made navigation impossible without visual reference to ground features. The bombers marked objectives with accuracy that suggested they possessed navigational aids superior to anything Germany had fielded. Intelligence reports mentioned mysterious new equipment, but captured air crews provided nothing. British crews operated under strict orders regarding new radar technology. Knowing that capturing an intact device could compromise the Allied superiority that had taken years to develop, crews were briefed that H-2S equipment was so valuable that its loss could change the war's course. Instructions were clear: reveal nothing, even under interrogation. The self-destruct charges installed in H-2S units were designed to trigger automatically on severe impact, or could be manually activated if capture seemed imminent. In December 1942, German signals intelligence detected unusual radio emissions from RAF bombers during raids. The signals were pulse transmissions at frequencies around 3 GHz, corresponding to wavelengths near 9 centimeters. German radio engineers who examined the intercept reports dismissed the initial findings. No one could generate useful power at such frequencies, the physicists insisted. The laws of physics made high-power centimetric radar impractical. The emissions must be some form of electronic countermeasure, perhaps a decoy transmitter, or possibly navigational beacons being interrogated by airborne receivers. They couldn't be operational radar because that would require power outputs German theory indicated were unachievable. On January 30, 1943, RAF Bomber Command conducted its first operational mission using the new H-2S ground mapping radar. Aircraft equipped with the centimetric radar from Pathfinder Force marked targets in Hamburg. Only 6 aircraft completed the marking mission, as 7 had to turn back with technical difficulties. The raid succeeded despite weather conditions that would have scattered conventional bombing. Observers noted the precision of the attack despite 10/10 cloud cover. The Pathfinders had marked the target with pyrotechnic indicators, and 100 Lancasters that followed bombed using these visual markers. For the first time, RAF bombers had found and marked a target in complete darkness and total cloud cover using only electronic navigation. The Luftwaffe achieved several interceptions during the Hamburg raid. One bomber was shot down, but the H-2S equipment aboard was destroyed in the crash and subsequent fire. German investigators found fragments of unusual radio equipment in the wreckage, but nothing that revealed the system's full capability or operating principles. They were looking at pieces of the most advanced radar technology in existence and did not recognize what they were seeing. 4 days later, on the night of February 3, 1943, the technological revelation arrived in a field near Rotterdam. The RAF conducted a raid on the Pernis oil refineries. Short Stirling Mark TA-1 bomber R926C4, serial number MGL, nicknamed Life for Love, from No. 7 Squadron Pathfinder Force, was returning from a bombing mission to Cologne when it was intercepted. Oberfeldwebel Frank of 2 NJG-1, flying a Messerschmitt Bf-110 from Gilzer Ryan Airfield, closed on the bomber in darkness. Ground-controlled interception using Würzburg radar had vectored the night fighter to the bomber's position. Feldwebel Wilhelm Goethe, Frank's radar operator, confirmed the target on their Liechtenstein airborne radar. The engagement was textbook. Frank positioned his Bf-110 below and behind the Stirling, in the blind spot where the bomber's defensive guns couldn't engage. A burst from the upward-firing cannon struck the bomber's fuselage and wing. The Stirling went down trailing fire, crashing at EO221 hours near the village of Humstead, approximately 3 kilometers from the crash site. The impact was severe, but not catastrophic. German recovery teams reached the crash site before dawn. 5 crew members had been killed in the crash, including squadron leader William Arthur Smith. 2 crew members survived and were taken prisoner. In the shattered nose section of the bomber, recovery personnel found equipment unlike anything in German experience. A rotating parabolic antenna, barely 60 centimeters in diameter, was connected to an electronic chassis that included a circular cathode ray tube display showing a plan position indicator format. The display unit had been destroyed in the crash, its glass tube shattered and internal components damaged beyond repair. But the transmitter section survived largely intact, protected by its robust copper construction. At the heart of the transmitter was that copper cylinder, machined with extraordinary precision, containing 8 symmetrical cavities arranged around a central cathode. The device bore British military markings and the designation CV-64. It was sealed, self-contained, with nothing beyond the primary electrical feed and a simple output coupling extending outward. The engineering was elegant, almost deceptively simple in appearance, yet the precision of manufacturing was immediately apparent, even on initial examination. This wasn't experimental equipment hastily assembled in a laboratory. This was production hardware designed for reliability and manufactured to exacting standards. General Lieutenant Wolfgang Martini, head of the Luftwaffe's signals intelligence, arrived at the crash site later that morning. Martini wasn't merely an administrator, but a trained engineer who understood radar technology. He had followed German radar development closely and was familiar with the theoretical limitations that had guided German research priorities. When he examined the captured equipment, he understood immediately that this was significant. The equipment was compact beyond anything German radar could achieve. The antenna was far too small for operation at frequencies Germans considered practical for high-power applications. Yet this was clearly sophisticated technology, not some experimental oddity that had failed under operational conditions. This was a working system that had been operating successfully when the bomber was shot down. Martini ordered the equipment transported under armed guard to Telefunken Berlin laboratories. The Magnetron was packed with extraordinary care. Guards accompanied the transport throughout the journey. The importance of the capture was immediately recognized at the highest levels of Luftwaffe command. This wasn't routine battlefield salvage, but a potential intelligence windfall that could reveal Allied technological capabilities. Professor Leo Brandtz received the recovered components on February 3rd at Telefunken's facilities in Berlin-Tempelhof. Brandtz, born in 1908, had worked as a high-frequency engineer at Telefunken since 1932. He was recognized as one of Germany's leading experts in radio frequency technology. His team worked through the night of February 3 to 4, meticulously documenting the device before attempting any testing. Every dimension was measured, every component was photographed from multiple angles. Detailed sketches were made of the internal structure visible through inspection ports. X-ray examination revealed the internal cavity structure and cathode assembly. The team worked with scientific precision, documenting everything because they understood they might have only one opportunity to examine this technology. What they found in those initial hours stunned them. The magnetron was a sealed unit, entirely self-contained, with no external magnets. German magnetron designs, including Hollmann's patented versions, required separate powerful electromagnets to generate the necessary magnetic field. These electromagnets were large, heavy, and required substantial electrical power. This device had permanent magnets built into its structure, integrated directly into the copper block housing. The magnets appeared to be made from cobalt steel alloys, materials that provided magnetic field strength German researchers had considered impossible to achieve with permanent magnets. The engineering was elegant to the point of appearing simple, but the precision required was extraordinary. Tolerances were measured in hundredths of millimeters. The 8 cavities were machined into solid copper blocks, not assembled from separate components. Each cavity was identical to the others within measurement precision. The cathode, running along the central axis, was coated with an oxide compound that German researchers recognized as an electron-emitting surface, but of a type German industry had not successfully manufactured. The vacuum seals used techniques that German manufacturers had attempted but not mastered for production units. Every gasket, every junction, every mechanical interface showed evidence of manufacturing processes refined through extensive production experience. On February 4th, Brandtz's team prepared to power the magnetron. They built a custom pulse generator to provide the high-voltage electrical pulses needed for operation. The team had no documentation, no operating instructions, no specifications. They had to infer the operating parameters from examination of the device and from general principles of magnetron operation. They expected, based on German experience with magnetron development, perhaps 100 watts output at best, possibly at frequencies around 500 MHz. When the magnetron was powered for the first time in a German laboratory, it produced approximately 10 kilowatts of pulsed power at precisely 3 GHz. The output was stable, repeatable, and far exceeded what German theory predicted as possible. The measurement instruments available in the laboratory were designed for much lower power levels. They had to improvise measuring techniques, using attenuators to reduce the signal to levels their equipment could handle, then calculating back to determine the actual output power. Every measurement confirmed the same incomprehensible reality. This thumb-sized device generated more microwave power than German laboratory equipment filling entire rooms could produce, and it did so with an efficiency that German theory suggested was unattainable at these frequencies. Brandtz wrote in his initial report, preserved in German archives and later captured by Allied intelligence teams, that the British had achieved in practice what German mathematics declared impossible. The report's tone was professional, clinical even, but the implications were clear to anyone who read it. Germany's understanding of microwave physics was incomplete. The theoretical frameworks that had guided German research had led them away from a technology that wasn't only practical, but had been in operational use by the enemy for an unknown period. Engineers measured the magnetron's performance over several days of testing. The output frequency was remarkably stable, varying less than 1% across multiple tests. The frequency stability was achieved through the physical dimensions of the cavities themselves, which acted as resonant structures. German magnetrons, using Hollmann's design, suffered from frequency drift as the device heated during operation, with thermal expansion changing the electrical properties of the oscillating system. The British design minimized this through careful engineering of the mechanical structure and choice of materials with appropriate thermal expansion coefficients. Every measurement revealed another layer of sophisticated engineering. The wavelength was equally shocking from a military application standpoint. 9 centimeters corresponded to 3 gigahertz frequency. This wavelength meant that a small antenna could provide resolution that would require antenna arrays tens of meters across at frequencies Germany used. The implications for airborne radar were immediate and devastating. The British could build radar systems compact enough for single-engine fighters, with resolution fine enough to detect individual buildings from high altitude. The British had cracked something extraordinary with centimetric wavelengths. These shorter waves could paint pictures of the coastline below with stunning clarity, rendering rivers and cities in crisp detail. Terrain features emerged from the radar display with a precision that made the longer wavelengths the Germans relied on look absolutely primitive by comparison. They could spot submarine conning towers cutting through dark water. They could intercept night fighters sliding through the black sky. They could track ships with an accuracy that left German radar capabilities looking decades behind. Yet the German radar establishment had written off centimetric wavelengths as impractical. The fundamental problem was simple enough, or so they'd believed. Nobody could generate sufficient power at those shorter frequencies. High-power microwave generation seemed theoretically impossible, a wall that couldn't be climbed. Then the British broke through that wall in February 1940. 2 men at Birmingham University, John Randall and Harry Boot, built their first working prototype. It produced 400 watts at 9.8 centimeter wavelength. By May that same year, they'd pushed the output past 1 kilowatt. General Electric engineers working at Wembley took it further. By late 1940, they'd cranked the output up to 10 kilowatts. A year later, production magnetrons were delivering over 100 kilowatts in pulsed mode. On February 5, 1943, Berlin witnessed a meeting unlike any other. The site was Luftwaffe headquarters, and the classification level was absolute. The room filled with faces that mattered. General Ottmar Martini sat present. Professor Brandt took his place. Representatives from Telefunken, Gamer, and other major German electronics firms filed in. Air defense commanders arrived. Luftwaffe technical staff settled into their seats. The energy in that room was heavy. People sensed something was terribly wrong. Brandt laid out his findings methodically. The technical language was precise, the measurements exact. But there was no escaping the conclusion, staring everyone in the face. The British cavity magnetron wasn't an improvement. It wasn't an incremental step forward. It was a complete technological leap, a fundamental breakthrough that Germany had somehow missed entirely. German researchers understood the basic principles. Patent records proved it. Some scientists had actually worked on magnetron designs. But German research had walked away from high-power microwave development because the mathematical models said it couldn't work within reasonable timescales during wartime. Resources were stretched impossibly thin. Industry was groaning under the strain. The priority went to squeezing better performance from existing systems rather than chasing speculative technologies that the physicists insisted wouldn't work anyway. The British hadn't just solved the engineering puzzle. They were already operating centimetric radar in the field. They'd been doing it for months, possibly longer. Germany sat convinced that such technology was either theoretically impossible or at minimum years away from any practical use. The conference examined what intelligence had gathered about British radar operations. The Würzburg system had successfully intercepted numerous RAF bombers. Recovery teams investigating wreckage from aircraft shot down before January 1943 found no sign of advanced radar equipment. This suggested the deployment might be recent, but other intelligence reports painted a grimmer picture altogether. U-boat commanders were describing something disturbing. Aircraft appeared suddenly in conditions where detection should have been absolutely impossible. 6 Marine intelligence had noticed something alarming. Allied success in locating surface submarines kept climbing. Luftwaffe bomber crews reported being intercepted by British night fighters far more often than made any sense. The conference participants started connecting these scattered intelligence pieces. The picture that emerged was deeply troubling. The British hadn't developed one radar system. They'd created an entire ecosystem of applications. Ground mapping radar for bombers finding their targets. air-to-surface vessel radar for hunting submarines, airborne interception radar for night fighters stalking German bombers, possibly gun-laying radar for anti-aircraft defense. Every application drew from the same fundamental technology, the cavity magnetron, adapted for different military purposes. The British had achieved not one breakthrough, but an entirely new category of radar technology, while Germany was still refining its older, longer wavelength systems. The recovered device received the designation Rotterdam Gerät, the Rotterdam device, named after the crash location that had delivered it to German hands. The response was immediate. A working group formed right away. They called it the Arbeitsgemeinschaft Rotterdam, abbreviated AGR. 3 objectives defined their mandate. First, understand how the British magnetron performed so exceptionally well. Second, develop countermeasures to protect German forces from centimetric radar. Third, start building German versions of equivalent technology to close the gap the British had opened. Each goal carried substantial obstacles. Each would grow harder as the war situation deteriorated. Understanding the magnetron required reverse engineering manufacturing processes Germany had never developed. The device used oxide-coated cathodes that demanded specific materials and particular processing techniques. German vacuum tube manufacturers had tried producing similar cathodes. Results had been inconsistent. The British had solved those manufacturing problems through years of steady development and production experience. Germany would need to match that from scratch. The permanent magnets required cobalt, a strategic material in desperately short supply. Before invading the Soviet Union, Germany had received cobalt from Soviet sources. That supply vanished. Turkish imports helped partially, but quantities remained insufficient. Even vacuum sealing techniques were foreign to German manufacturers. The magnetron had to hold high vacuum over long operational life while withstanding vibration, temperature swings, and the mechanical stress of actual use. German vacuum tube manufacturing relied on glass envelopes sealed with metal-to-glass connections. Techniques refined over decades for radio tubes. The British magnetron used all-metal construction with ceramic insulators. This required completely different manufacturing approaches. Every single aspect of the device showed engineering refinements that came only from extended production experience. On February 22nd and 23rd, the Arbeitsgemeinschaft Rotterdam held its first formal meeting at Telefunken's Berlin offices. The room held representatives from Germany's electronics industry, Luftwaffe technical services, university researchers, and radar specialists from operational units. They examined the magnetron with exhaustive care, passing it around the table, taking measurements with calipers and micrometers, making sketches, discussing manufacturing challenges. The atmosphere was professionally reserved. These were experienced engineers and physicists who knew exactly what they were seeing and what it meant. The verdict was sobering. Germany could copy the British design. Given proper tooling and enough time, German machine shops could manufacture components to specification. Materials scientists could develop equivalent cathode coatings. Metal workers could create permanent magnets approaching British performance. But production would require pulling resources away from existing programs already struggling to meet Wehrmacht demands. Precision component manufacturing capacity was strained to the breaking point. Machine tools ran multiple shifts. Skilled workers were disappearing into military service. Raw materials were allocated months in advance to existing priority programs. Using brand-new production processes for unfamiliar technology would take many months minimum, possibly over a year, before meaningful quantities could actually be produced. Dr. Otto Hatchenberg, a young Telefunken engineer assigned to the AGR project, later recalled the atmosphere of those early meetings. In 1973, Woodruff Sullivan interviewed him for the National Radio Astronomy Observatory, research that would eventually contribute to Sullivan's book on early radio astronomy. Hatchenberg had worked recovering and analyzing radar equipment from crashed Allied aircraft during the war. He described the psychological impact of examining British technology in stark terms. "We were examining equipment that proved British engineers had solved problems we had declared impossible," he recalled. Every aspect of the design showed thoughtful engineering, matured through experimentation we had never conducted. This wasn't laboratory prototype equipment thrown together by researchers. This was production hardware, meaning the British were manufacturing these devices in quantity. We were studying what appeared to be the third or fourth generation of their development, while we hadn't even started serious work on the first generation. The revelation deepened when interrogators spoke with the surviving crew members from the downed Sterling. Initially, the two prisoners gave only name, rank, and serial number, as required by the Geneva Convention. They'd been extensively briefed on H-2S importance. They understood that no information should be disclosed under any circumstances. RAF Bomber Command had emphasized during their briefings that H-2S represented years of British research investment and that German capture of the system could damage Allied bombing effectiveness. However, over subsequent days and weeks, German interrogators skillfully extracted key details. The Luftwaffe Interrogation Center at Oberursel near Frankfurt employed experienced interrogators using sophisticated psychological techniques. They didn't resort to physical coercion, which was generally counterproductive with Allied aircrew and violated international agreements anyway. Instead, they employed isolation, seemingly casual conversation, planted false information to trigger corrections, and careful psychological pressure applied over extended time. From these interrogations, German intelligence learned crucial information. The system was called H-2S, though the prisoners didn't know where the name came from. It provided a map-like display of ground features below the aircraft, showing coastlines, cities, rivers, and terrain. The radar had been operational since late January 1943, only days before this particular aircraft was shot down. Most alarming was that this wasn't experimental equipment assigned to a handful of select aircraft. Bomber Command was fitting H-2S to the entire Pathfinder force, with plans to eventually equip all heavy bombers. The crew's information suggested British production capacity could manufacture these devices in hundreds, possibly thousands. The scale of British centimetric radar deployment became clearer as intelligence accumulated through February and March 1943. Multiple information sources began converging into a comprehensive picture. Signals intelligence detected H-2S transmissions from increasing numbers of RAF bombers. The distinctive pulse characteristics and frequency range became identifiable. Kriegsmarine reports documented climbing U-boat losses in the Atlantic. Submarines were being attacked by aircraft in conditions where previous generation radar should have made detection impossible. Boats were being caught surfaced at night in complete darkness, attacked before they could crash dive to safety. The Magnetron technology wasn't limited to bombing radar. Coastal Command aircraft were using centimetric ASV Mark III radar to detect surfaced submarines. The same cavity magnetron, providing 9 cm wavelength for H-2S ground mapping, could detect submarine conning towers and periscopes at ranges longer wavelength radar couldn't match. The narrow beam width possible at centimetric wavelengths provided angle accuracy sufficient to guide aircraft directly to submarines before they could detect the threat using German METOX radar detectors, which were tuned to detect the longer wavelengths of ASV Mark II radar. U-boat losses in the Atlantic had climbed mysteriously throughout late 1942 and early 1943. Admiral Karl Dönitz, commanding U-boat forces, had noted with concern that submarines were being caught on the surface with increasing frequency. U-boat commanders reported being attacked by aircraft that appeared suddenly, offering no warning to allow time for diving. The METOX detector, which had previously given effective warning of approaching ASV-equipped aircraft, was failing against these newer systems. The explanation was now clear. British aircraft were hunting submarines using ASV Mark III centimetric radar that German boats couldn't detect with existing equipment. British night fighters carried centimetric AI radar designated AI Mark VIII, far superior to German systems. Liechtenstein Fugue 202 operated at 61 cm wavelength and required large 32-element Matratze antenna arrays that created significant aerodynamic drag and reduced aircraft speed by 20 to 30 km per hour. The later Liechtenstein SN2 used lower frequency to avoid British jamming, but required even larger 8-element Hirschgeweih antenna arrays that slowed aircraft by 50 km per hour. British centimetric AI used compact dish antennas barely 1 meter in diameter, and provided superior target resolution with minimal aerodynamic penalty. RAF night fighters, equipped with AI Mark 8, had been decimating German bomber raids over Britain throughout early 1943. Luftwaffe intelligence had attributed this to improved ground-controlled interception tactics and searchlight cooperation. The real reason was radar that could locate German bombers with precision German technology couldn't match. On March 1, 1943, the situation took an ironic turn that would have been almost comedic if the stakes weren't so serious. During a major RAF raid on Berlin, British bombs struck the Telefunken facility where the Rotterdam Gerrit was being analyzed. The building suffered severe damage. The captured magnetron was destroyed, reduced to fragments by the explosion. The working group lost its only complete sample just as they were beginning to understand its construction and preparing to attempt production copies. The loss was devastating. Weeks of careful analysis, documentation, and reverse engineering planning seemed suddenly wasted. Then, extraordinarily, that same raid provided a replacement. A Handley Page Halifax the Settings W7877 from No. 35 Squadron was shot down by Lieutenant August Geiger near Markale in the Netherlands. The Halifax crashed with another H-2S unit aboard. Recovery teams found the equipment in better condition than the Rotterdam device, with much of the display system intact, along with a complete magnetron. The odds of losing one sample to bombing and gaining another on the same night were astronomical, but it illustrated the scale of British H-2S deployment. RAF Bomber Command was equipping aircraft with this advanced technology at a rate suggesting substantial manufacturing capacity existed. German scientists immediately set to work analyzing the second unit. The device was essentially identical to the Rotterdam Gerrit, confirming these were production units manufactured to standard specifications rather than hand-built prototypes. Telefunken was tasked with producing German copies designated LMS-10, based on the British CV-64 design. LMS stood for Laufzeit Tube mit Magnetsteuerung, transit time tube with magnetic control. The copying process revealed layer upon layer of British engineering sophistication that would challenge German manufacturing capabilities. Every component required manufacturing processes that German industry had to develop from scratch or significantly improve. The cavity dimensions had to be machined to extraordinary precision. Tolerances of 0.02 mm or better were required to achieve proper resonance at the operating frequency. German machine shops, accustomed to tolerances of 0.1 mm for most radar components, weren't equipped for such precision work on the required scale. New milling machines with better bearings and more rigid construction had to be procured. Precision measuring instruments had to be calibrated. Machinists had to be trained in techniques they'd never needed before. The entire manufacturing process required improvements German industry struggled to implement while simultaneously dealing with Allied bombing disruption. The oxide-coated cathodes required materials and processes that German chemical industry hadn't perfected. British cathodes used barium and strontium oxide coatings applied at high temperature in precisely controlled atmospheres. The coating had to be uniform, adherent, and produce consistent electron emission properties. German attempts to produce similar cathodes had achieved partial laboratory success, but hadn't achieved the consistency needed for production units. British manufacturers clearly had years of production experience refining the process. Germany was starting from laboratory-level understanding and attempting to reach production capability under wartime pressures. Britain had been working with American firms, particularly Western Electric and General Electric, that had decades of experience with vacuum tube manufacturing for communications and broadcasting. When Britain shared cavity magnetron technology with the United States through the TESAD mission in September 1940, American manufacturers had rapidly scaled up production using manufacturing expertise gained through years of commercial vacuum tube production. Germany had a strong vacuum tube industry, but it was oriented toward glass envelope construction using metal-to-glass sealing techniques. The all-metal magnetron with ceramic insulators required different manufacturing approaches that German industry was attempting to develop in parallel with production efforts. The permanent magnets presented perhaps the greatest material challenge. British Magnetrons used cobalt steel alloys, likely Alnico type, creating powerful permanent magnets integrated directly into the tube structure. These magnets provided magnetic field strength of several thousand Gauss, necessary for proper magnetron operation. Germany faced critical cobalt shortages affecting all high-temperature alloy production. Cobalt was essential for turbine blades in aircraft engines, cutting tools for machine shops, and various steel alloys used in weapons production. Before the war, Germany had imported cobalt primarily from Belgian Congo and Canada. Sources cut off when war began. Limited supplies came from Finland and Turkey, but quantities were insufficient to meet all military needs. Diverting cobalt to magnetron production meant reducing availability for other military necessities, each with its own priority claim on scarce resources. German planners faced impossible allocation decisions. Aircraft engine manufacturers needed cobalt for turbo supercharger components, allowing high-altitude operation. Machine tool manufacturers needed cobalt steel for cutting tools maintaining hardness at high temperatures. Tank manufacturers needed cobalt for armor-piercing ammunition. Every ton of cobalt allocated to magnetron magnets was a ton unavailable for these competing uses. German engineers experimented with alternative magnetic materials, including various iron-nickel alloys and chrome-steel combinations. None provided the field strength required for optimal magnetron performance. Electromagnets could provide sufficient field strength, but added weight, required separate power supplies, and introduced reliability issues. The elegance of the British design, with integrated permanent magnets requiring no power and having no failure modes, was impossible to replicate with German materials. In a bitter irony that illustrated the desperate state of German radar development, engineers began salvaging permanent magnets from other crashed British aircraft to complete their magnetron copies. German production units were being completed using British-manufactured components cannibalized from battlefield salvage, a situation that underscored the industrial limitations Germany faced. By May 1943, Telefunken had completed 4 LMS-10 magnetrons, painstaking copies of the British CV-64 design. These represented 3 months of intensive work by some of Germany's best engineers and consumed resources from precision machine shops, chemical plants, and materials suppliers across German industry. 4 tubes total. Meanwhile, according to captured documents recovered after the war, Britain was producing approximately 200 cavity magnetrons per month by mid-1943. American production was reaching similar levels. The contrast couldn't have been more stark. The gap between Germany and the Allies wasn't simply a matter of understanding the science. It ran far deeper, rooted in industrial capacity and resource availability. German physicists grasped the underlying principles. German engineers could sketch equivalent designs on paper and blueprints looked sound. But translating those designs into working hardware at scale presented an entirely different challenge. Germany lacked the manufacturing infrastructure to produce such sophisticated equipment while simultaneously maintaining output of existing military systems the armed forces depended on daily. Throughout spring and summer of 1943, the Arbeitsgemeinschaft Rotterdam convened regularly, members hammering out detailed production schedules and requesting resource allocations. They wrestled with manufacturing bottlenecks at every turn. Yet genuine progress remained frustratingly elusive as Germany's industrial foundation crumbled under relentless Allied bombing campaigns and resource exhaustion that seemed to deepen by the week. While that effort continued, the AGR pursued a parallel path. If Germany couldn't immediately match British capabilities, perhaps they could detect and neutralize the advantage those capabilities provided. A countermeasures program targeting centimetric radar offered a potentially faster route than building equivalent systems from scratch. The detection approach proved surprisingly tractable compared to manufacturing magnetrons. Crystal detectors tuned to 9-centimeter wavelengths could intercept H2S transmissions from considerable distances away. German factories possessed the industrial knowledge to manufacture crystal detectors using established processes. No revolutionary materials were required. No exotic production techniques needed development. By April 1943, prototypes had taken shape that night fighter crews could actually carry aloft. Engineers designated the system FUG 350 Naxos Zed, naming it after the Greek island of Naxos. The device featured a rotating direction-finding loop antenna housed in a teardrop-shaped fairing mounted on aircraft fuselages. The receiver covered frequencies between 2,500 and 3,450 MHz, encompassing the H-2S operating range. At roughly 35 kilometers detection distance, it offered sufficient range to help night fighters locate bomber streams that would otherwise remain invisible in the darkness and clouds overhead. Naxos furnished night fighter crews with directional information toward RAF bombers transmitting H-2S signals. The system couldn't deliver precise range or bearing measurements, but it allowed fighters to home toward emission sources before switching to visual contact or Liechtenstein AI radar for the final intercept. Operational service began in September 1943, first seeing combat use on September 2nd. As pilots grew accustomed to the technology, German night fighter kills climbed noticeably, pilots treating British radar transmissions as beacons that revealed bomber positions. Yet Naxos remained fundamentally reactive, a response to British capability rather than an equivalent German achievement. It depended entirely on British bombers continuing to transmit. Should the British deactivate their radar or switch frequencies, Naxos became useless overnight. British intelligence organizations learned of Naxos through signal intercepts and interrogating captured German crews. RAF leadership grew worried that H-2S might actually be giving German fighters bomber positions, potentially causing losses that outweighed navigation advantages. Analysts conducted thorough comparisons of loss rates before and after Naxos deployment. Surprisingly, losses actually declined slightly following Naxos introduction, likely because H-2S-equipped aircraft navigated more precisely and spent less exposure time crossing German territory. The RAF determined H-2S benefits justified the risks and maintained full deployment. British engineers immediately attacked the problem, developing countermeasures, including the 3-centimeter H-2S Mark III, which operated outside Naxos detection range. German indigenous centimetric radar development limped forward throughout 1943 and 1944 as mounting obstacles accumulated. Telefunken pursued an airborne interception system designated FUG 240 Berlin, built around magnetron technology derived from captured British designs. The intention was equipping German night fighters with centimetric AI capability matching British systems. Siemens developed a ground-based jammer called Roderick, designed to disrupt H-2S operations through powerful transmissions on H-2S frequencies. GEMA investigated centimetric early warning systems intended to replace Freya with more capable technology. Every project confronted identical fundamental constraints that proved insurmountable. Limited manufacturing capacity meant that even when prototypes functioned successfully, production couldn't scale up rapidly. German industry was already operating at absolute maximum, churning out existing radar systems, communications equipment, and countless electronic components. Absolutely no spare capacity existed to absorb new production demands. Critical material shortages intensified throughout 1943 and 1944, as Allied bombing ravaged supply chains and eliminated access to essential sources: cobalt for magnets, tungsten for transmitter tubes, specialized steel alloys for waveguide components. Even fundamental materials like copper and aluminum became scarcer month by month. Inexperience with high-frequency techniques meant German engineers were advancing through trial and error as they developed systems. Components British engineers manufactured routinely were exotic rarities in Germany, each requiring dedicated development efforts. Crystal mixers for receivers needed germanium crystals ground and mounted with demanding precision that German industry struggled to achieve consistently. The crystals required exact contact points, creating metal semiconductor junctions with specific electrical characteristics. British manufacturers, working alongside American partners, had long since standardized crystal detector production. German manufacturers were still perfecting laboratory methods. Waveguide components demanded machining precision exceeding normal German manufacturing standards. These hollow metal tubes conducted microwave energy and required exact internal dimensions to propagate specific frequencies without excessive signal loss. Surface finishes had to meet more stringent requirements than lower frequency components. German machine shops consistently fell short of specifications. Even relatively uncomplicated items like coaxial cables, designed for centimetric wavelengths, remained in desperately short supply. Cables required precise conductor spacing, maintained throughout their length, coupled with low-loss dielectric materials and adequate shielding. German cable manufacturers accustomed to lower frequencies struggled achieving necessary performance levels. Intelligence reaching German air defense revealed how vast the gap had become. The TESARD mission to America in September 1940 had demonstrated cavity magnetron technology to American scientists during Washington meetings. That demonstration occurring on September 19, 1940, at Alfred Loomis's apartment in the Wardman Park Hotel, had shocked American researchers. The British magnetron produced 100 times more power than anything Americans had achieved at centimetric wavelengths. American scientists immediately comprehended the technology's military potential. American industrial capacity mobilized rapidly to exploit it. MIT established the Radiation Laboratory in November 1940 specifically for developing radar systems using cavity magnetron technology. The laboratory expanded to over 4,000 scientists and engineers by 1943, an organizational scale Germany could never approach. Contracts cascaded to dozens of American manufacturers for magnetron production. Bell Telephone Laboratories, Western Electric, Westinghouse, General Electric, RCA, and numerous smaller firms manufactured magnetrons and radar components. By 1943, American industry produced magnetrons at thousands monthly, equipping American forces while supplying Britain through Lend-Lease. The magnetron German scientists examined so carefully represented merely one among tens of thousands in production. America integrated centimetric radar into virtually every military application imaginable. Gun-laying systems like the SCR-584 used centimetric radar directing anti-aircraft fire with previously impossible accuracy. Naval fire control systems employed centimetric radar spotting shell splashes and directing gunfire at targets beyond visual range. Airborne early warning systems, using centimetric radar, detected enemy aircraft at ranges exceeding 150 kilometers. Precision bombing aids like the Norden bombsight integrated centimetric radar with autopilot systems for automatic bombing through cloud cover. Each application represented development programs with budgets measured in millions of dollars, exceeding Germany's entire radar research allocation across all programs combined. British centimetric radar production had expanded from laboratory prototypes in 1940 to industrial-scale manufacturing by 1942. The GEC facility at Wembley manufactured early prototype magnetrons that traveled to America aboard the TESARD mission. By 1942, GEC, EMI, Ferranti, Standard Telephones and Cables, and other British firms produced magnetrons by the hundreds monthly. The cavity magnetron had transformed into a production component with standardized designs, interchangeable parts, and quality control procedures guaranteeing consistent performance batch after batch. British manufacturers had solved the production engineering problems that German industry continued attempting to overcome. German magnetron development remained trapped in the experimental stage, producing hand-built prototypes requiring individual tuning and adjustment. Every German magnetron was essentially unique, assembled by skilled technicians adjusting cavity dimensions, cathode positioning, and magnetic field strength until performance reached specification. This was laboratory practice, not industrial production. British magnetrons rolled off production lines with guaranteed performance specifications ensured by manufacturing process control. Precision machining held dimensions. Controlled processes applied cathode coatings, yielding consistent results. Manufacturers produced magnets to specifications ensuring proper field strength. Testing verified performance, but individual tuning wasn't required because manufacturing processes ensured consistency themselves. The distinction represented far more than mere years of development time. it reflected fundamentally different approaches to industrial organization and quality control. As German scientists wrestled with magnetron production, they simultaneously confronted how comprehensively they'd fallen behind in related technologies. Cavity magnetrons enabled compact centimetric radar, but effective systems demanded other equally advanced technologies. British radar incorporated plan position indicator displays, circular cathode ray tube screens presenting map-like target presentations with radar at center, and targets appearing at proper range and bearing. This proved far more intuitive than A-scope displays showing range and bearing separately. German radar relied on A-scope technology because it represented established practice, well understood and producible. Developing PPI displays required specialized CRT tubes, deflection circuits, and signal processing that German radar engineers had only begun investigating seriously in 1943. British systems incorporated automatic tracking, using servo mechanisms maintaining antenna lock on targets without manual operator intervention. Once acquired, radar tracked automatically, maintaining lock through turns and maneuvers. German systems demanded manual tracking by skilled operators, constantly adjusting controls, keeping targets centered. Automatic tracking required feedback control systems, position servos, and signal processing techniques German industry hadn't widely deployed. The technology existed in German laboratories, but production systems remained manually operated. British radar used TR switches, transmit-receive devices, allowing single antennas both transmitting and receiving by isolating receivers during transmission pulses. This eliminated requirements for separate transmit and receive antennas, simplifying antenna systems and improving performance. German systems typically employed separate antennas or crude switching methods, proving less effective. British TR switches used gas discharge tubes, switching in nanoseconds, protecting sensitive receivers from kilowatts of transmitter power. German engineers had begun developing similar components in 1943, but remained years behind practical implementation. Most troubling was how this technological gap had developed largely undetected by German intelligence. Germany possessed excellent scientists, many educated at world-class universities. Germany had capable engineers with strong theoretical foundations. Germany had substantial industrial capacity built through 1930s rearmament programs. Yet Britain, with significantly smaller industrial base and fewer total resources, had achieved decisive technological superiority in the war's most militarily significant electronic technology. Post-war analysis revealed how this occurred, exposing important lessons about technology development and strategic planning. The explanation traced to different strategic decisions made years before conflict began. Britain had prioritized radar development from 1935 onward under Robert Watson Watt's direction and the Committee for the Scientific Survey of Air Defense. Substantial government funding flowed toward radar research. The chain-home early warning system was constructed despite enormous expense and technical challenges. Research infrastructure was created specifically for radar development, including the Bawdsey Research Station and later the Telecommunications Research Establishment. Specialists underwent systematic training. Industrial capacity was established with government support. By 1939, Britain had invested years of effort and substantial resources in radar technology. Germany had also developed radar systems during the 1930s, actually deploying operational systems before Britain in certain instances. Freya and Würzburg radars represented excellent systems, but Germany hadn't made radar development the absolute top priority that Britain had. German radar programs competed against numerous other military technology programs for funding and resources. When conflict began, German industry focused on producing existing systems rather than exploring new approaches. Blitzkrieg victories from 1939 through 1941 seemed validating German equipment and tactics, reducing pressure to develop fundamentally new technologies. The Hitler Decree of 1940, limiting research funding to projects promising results by 1942, particularly devastated long-term radar development. Cavity magnetron development required patient experimental work spanning multiple years. Gradual manufacturing process refinement couldn't be accelerated. Systematic testing was essential for understanding behavior at frequencies existing theory inadequately explained. Such research couldn't promise definite results within the 2-year framework the decree mandated. German programs exploring centimetric wavelengths faced defunding or reduced priority during 1940 and 1941, precisely when British programs achieved breakthrough results. German research facilities shifted toward improving existing systems rather than developing fundamentally different capabilities. Würzburg improvements, Freya range extensions, Liechtenstein airborne radar development all received priority because they promised near-term operational improvements. Longer-range research into fundamentally different approaches was postponed until after anticipated victory, which German leadership expected achieving through existing capabilities. The decision seemed rational considering German military success during 1940 through 1941 and apparent validation of German equipment and tactics. But it conceded technological initiative to Britain precisely when British desperation was driving innovation. By summer 1943, the comprehensive scope of Allied centimetric radar deployment became apparent to German air defense through accumulated intelligence from multiple sources. British H-2S enabled precision bombing through weather and darkness that previously scattered bombing effectiveness. More than 200 RAF bombers carried H-2S by mid-1943, with production continuing at rates equipping the entire heavy bomber force within approximately a year. Coastal Command ASV Mark III radar was making the Atlantic progressively more dangerous for U-boats, contributing to a crisis forcing Dönitz to temporarily withdraw U-boats from the North Atlantic in May 1943. RAF night fighters equipped with centimetric AI Mark V were inflicting unsustainable losses on German bomber forces attempting attacks on Britain, essentially ending the German strategic bombing campaign. American radar technology was advancing even faster than British, with development programs dwarfing British efforts in scale. The SCR-584 gun-laying radar using cavity magnetron technology and automatic tracking was achieving anti-aircraft effectiveness previously impossible. Naval surface search radars allowed American ships fighting effectively in darkness and poor visibility. Airborne early warning radar provided fleet protection against air attack. Each American system represented development programs with budgets and personnel exceeding Germany's entire radar effort. German post-war memoirs frequently drew Manhattan Project analogies. Germany had excellent nuclear physicists, including Werner Heisenberg, Otto Hahn, and others of international reputation. But Germany remained years away from atomic weapons, if such weapons could be constructed. German nuclear research had been fragmented, underfunded, and lacked the massive industrial mobilization characterizing the Manhattan Project. Similarly, Germany had excellent radar engineers and physicists, but was a decade behind in the specific technology dominating electronic warfare. The cavity magnetron gap wasn't merely technological. It represented comprehensive failure in scientific industrial mobilization for a technology whose military significance wasn't recognized until Britain had already achieved an insurmountable lead. German attempts closing the gap persisted through late 1943 and 1944, but circumstances grew increasingly unfavorable. Allied bombing was systematically disrupting German industrial production. The combined bomber offensive specifically targeted ball-bearing factories, aircraft plants, oil refineries, transportation networks, and electronics manufacturing facilities. Critical material shortages intensified as sources were cut off and stockpiles depleted. Romanian oil production faced threats. Swedish iron ore supplies diminished. Turkish chrome and cobalt deliveries became irregular. Every critical material encountered allocation difficulties. Skilled workers were being conscripted for combat units as military losses mounted and frontline units demanded replacements. Engineers and technicians were drafted, removing specialized knowledge from factories and laboratories. Training new workers consumed time Germany didn't possess. Quality suffered as experienced workers were replaced by hastily trained substitutes. Research facilities were being evacuated from cities vulnerable to air attacks, disrupting ongoing programs and dispersing teams. Telefunken facilities in Berlin faced multiple bombing attacks. The Arbeitsgemeinschaft Rotterdam itself had to relocate meetings to different locations as facilities were damaged or destroyed. The AGR continued meeting throughout 1943 and 1944, documenting progress and obstacles in detailed protocols that survived the war and provided historians insight into German radar development struggles. Meeting minutes revealed technical discussions of magnetron design, manufacturing problems, materials shortages, and mounting frustration with lack of progress. The protocols show competent engineers working under impossible conditions, understanding what needed accomplishing, but lacking resources and time to complete it. Production plans were developed showing how Germany could manufacture magnetrons in militarily significant numbers, provided materials were available, skilled workers could be retained, bombing didn't disrupt production, and sufficient time existed. None of those conditions could be satisfied. By early 1944, Telefunken had produced approximately 20 magnetron copies, compared to over 10,000 produced by British and American industry. Siemens had delivered a handful of Roderick jammers deployed at air defense sites around key targets, but their effectiveness remained limited. The Berlin airborne radar encountered extended testing problems with reliability and performance. Production of operational systems in militarily significant numbers remained perpetually 6 months away, a receding timeline as obstacles accumulated. In April 1945, as Allied forces overran German territory from east and west, Telefunken finally began delivering production Fug 240 Berlin night fighter radars. The system used German-built magnetrons based on captured British designs and provided capabilities roughly equivalent to British centimetric AI from 1942, 3 years earlier. Approximately 25 units were installed in Junkers Ju-88 night fighters. The war ended in May 1945 before the system saw significant combat use. 3 years after capturing the Rotterdam Garret in February 1943, Germany had produced a system equivalent to technology Britain had fielded operationally in 1942, and America had already surpassed by 1943. The reality of that decade-long gap in radar physics was far more than symbolic. It was concrete and measurable. When German engineers examined their own centimetric radar systems in 1945, they were looking at technology that matched British capabilities from the beginning of 1942. 3 years had passed on the calendar, yes, but the difference in technological trajectory ran much deeper than a simple timeline could capture. It reflected fundamental divergences in how each nation approached development, where they invested their industrial might, and what they believed was theoretically possible. After the fighting ended, Allied intelligence teams conducted thorough investigations. Their conclusions were definitive and supported by extensive documentation they'd recovered from German facilities. Dr. Otto Hachenberg had spent the war working on radar projects, including the Rotterdam magnetron program. After 1945, he became a respected radio astronomer and eventually a colleague of the very British scientists who developed the cavity magnetron technology he'd studied so intently during wartime. His post-war journey took him through several prestigious positions. From 1951 to 1961, he worked at the Heinrich Hertz Institute. In 1962, he became a professor at Bonn University. Then, from 1967 to 1978, he served as founding director of the Max Planck Institute for Radio Astronomy, where he played a crucial role in designing the 100-meter Effelsberg radio telescope. Over the years, when interviewed decades after the war, Hachenberg spoke with remarkable candor about Germany's failure, discussing it with the honesty of a professional scientist rather than defensiveness. During a 1973 interview, he reflected on what had happened. Germany, he explained, had known the basic principles. Holman had patented cavity magnetron designs back in 1935. The theoretical knowledge existed in scientific journals that German researchers could access. What Germany hadn't maintained was the steady, determined push to transform that theoretical knowledge into working hardware. The British had made it their business. They'd committed to developing cavity magnetrons. They'd pushed through experimental failures. They'd persisted when results looked discouraging. They'd kept going until success arrived. Germany had done the mathematics differently. Their theoretical models suggested the venture wouldn't work. When those calculations predicted failure, the research effort simply stopped. Later, when captured British equipment revealed what had actually been achieved, German scientists faced an uncomfortable truth. They'd given up years too early. By then, they were so far behind that even with full commitment, they couldn't close the distance before time ran out. The real problem, Hachenberg acknowledged, wasn't inferior scientific knowledge. It was a failure of will to pursue development when theory suggested it wouldn't pay off. The British had pursued it anyway. Allied intelligence operations after the war systematically documented what Germany had accomplished and where it had fallen short. Multiple organizations conducted these investigations. Teams examined German radar research facilities with meticulous care. They interviewed the scientists and engineers who'd worked on these programs. They studied the captured equipment and technical documents. The Combined Intelligence Objective Subcommittee sent investigators to industrial facilities and technical institutes. British intelligence conducted parallel examinations. Together, these efforts created a comprehensive picture. What emerged from these investigations was nuanced. German radar research showed sophistication and genuine excellence, where Germany had invested consistently and continuously. The Würzburg tracking radar was sophisticated engineering, effective within its frequency range. The conical scanning technique it used achieved accuracy that approached theoretical limits for that wavelength. The mechanical construction was solid and dependable. The operational practices were well thought out and practiced. The Freya early warning systems did their job effectively, with respectable range and reliable performance. German radar systems guiding anti-aircraft fire actually outperformed comparable Allied equipment using similar wavelength technology. Where Germany had pursued radar development without interruption, the results were respectable. Sometimes they were even superior to what the Allies were producing in equivalent categories. But when it came to centimetric wavelengths, German research had essentially stopped around 1940 and 1941. The investigators found German laboratories still equipped with Allied radar equipment, sitting there being analyzed when the war ended. German engineers were still trying to understand what the Allies had moved past. They were wrestling with 3-centimeter systems, while Allied development had already advanced to even shorter wavelengths. The lag wasn't because German scientists lacked intellectual capability. The problem was that German science had focused on different questions, while Allied science was solving the fundamental challenge that would define radar's entire development arc. The strategic consequences were profound and measurable in concrete ways. Centimetric radar opened up military possibilities that longer wavelength technology simply couldn't match. The Battle of the Atlantic swung decisively toward the Allies in 1943, fundamentally because aircraft from Coastal Command, equipped with ASV Mark III radar, could spot submarines that German U-boats couldn't escape from. Submarines got forced deeper, staying submerged more, which made them less effective and forced them to recharge batteries during daylight when visual spotting became possible. A dangerous time for any submarine. Strategic bombing improved progressively as H-2S and later H-2X systems with 3-centimeter wavelengths allowed crews to navigate accurately and bomb through weather that would have scattered earlier bombing runs in all directions. Night bombing accuracy jumped from miles of error to hundreds of meters. RAF night fighters with centimetric AI radar intercepted German bombers with devastating efficiency. The attacks on Britain became so costly and ineffective that by mid-1943, the Luftwaffe essentially stopped trying. German bombers couldn't counter advantages they couldn't duplicate because they lacked the equivalent technology. None of these successes depended entirely on radar. But in every instance, centimetric radar provided capabilities that German forces simply couldn't match effectively. Germany didn't possess the technology, and without it, they couldn't even develop effective defenses against capabilities they couldn't reproduce. The cavity magnetron itself represented a textbook example of technological surprise during wartime. Germany understood the theoretical foundations of how magnetrons worked. German scientists had researched magnetron designs and published their findings in international scientific journals. Hollmann's 1935 patent showed that German researchers grasped multi-cavity magnetron concepts. Yet when confronted with what British engineers had actually achieved, German technicians had to admit they were years behind in turning theory into practical high-powered devices operating at useful frequencies. The real shock wasn't that cavity magnetrons could work in principle, which German physicists accepted readily enough. The shock was discovering they could function at power levels and frequencies that German calculations had deemed impractical for actual military use. The British hadn't simply built better equipment through engineering superiority. They demonstrated that German understanding of what was technically feasible was fundamentally incomplete. German theoretical models had predicted magnetrons would become unstable and weak at centimetric wavelengths. Those models turned out to be wrong or based on incomplete understanding. British researchers, through relentless experimentation, found solutions to problems that German theoreticians had declared unsolvable. This represented more than engineering failure. It was a breakdown in scientific methodology, revealing the dangers of depending entirely on theoretical analysis without extensive experimental work to test those theories. The industrial side of this technological surprise was equally significant and strategically even more consequential. Eventually, German engineers learned how to build magnetrons that approached British performance levels. The LMS-10 magnetrons that Telefunken produced functioned comparably to the British CV-64 units they were modelled after. German scientists understood the physics. German engineers could replicate the designs successfully. What Germany couldn't achieve was matching the production capacity the British and Americans had built. The tens of thousands of magnetrons pouring out of British and American factories dwarfed German output, hundreds total across the entire war period. British and American magnetron production represented industrial mobilization for electronic warfare on a scale Germany never attempted and couldn't sustain, given their resource limitations and competing demands. These radar tubes were being manufactured using the same mass production methods and quality control systems used for artillery shells or aircraft engines. Quality control kept performance consistent. Standardization meant components could be swapped interchangeably. Production volume transformed specialized technology, requiring expert craftsmen, into a plentiful commodity distributed across all military services in countless applications. German radar remained specialized equipment built in limited numbers by skilled technicians working by hand. The decade gap wasn't simply measured in calendar years between British invention and German production capability. From the British breakthrough in February 1940 to German limited production in April 1945 was roughly 5 calendar years. But in terms of actual capability, German radar in 1945 matched what the British had achieved from 1941 through 1942, representing roughly a 3-year lag in development progression. This 3-year gap, though shorter in calendar time, reflected deeper problems in how development proceeded and how industrial production was organized. During those 5 calendar years, British and American radar advanced through multiple generational improvements. By 1945, British systems operated at 3-centimeter wavelengths, with H2S Mark III providing resolution detailed enough for mapping cities from the air. AI Mark X airborne interception radar could distinguish individual buildings. American systems included the APS-20 airborne early warning radar, with ranges exceeding 150 kilometers and capability to track numerous targets at once. Ground mapping radar like H2X showed resolution displaying individual streets and buildings. Gun-laying radars like the SCR-584 tracked aircraft automatically and directed anti-aircraft fire onto invisible targets through darkness and weather with accuracy that made German radar systems look primitive by comparison. German radar in 1945 was still trying to catch up to British capability from the middle years of the war, while Allied radar had leapt far ahead. Behind the technology stood thousands of scientists and engineers on both sides, working with genuine intelligence, serious dedication, and patriotic commitment. German radar engineers weren't incompetent. They were talented professionals with excellent theoretical training, laboring under increasingly difficult circumstances. They were trying to match technological achievements that demanded resources and infrastructure Germany no longer possessed by 1943 and 1944. British and American radar scientists weren't superhuman geniuses either. They were competent professionals who'd benefited from institutional decisions made years before to prioritize radar development and from industrial systems capable of turning laboratory breakthroughs into production hardware at scale. The difference in results flowed from differences in strategic choices about how to allocate resources, made years before the war even started. Differences in managing technology development. Differences in industrial capability and how it was organized. Britain had declared radar development a national priority back in 1935, when the technology was still immature and unproven. That early investment built expertise. It created infrastructure. It generated momentum. When war arrived, those advantages paid off spectacularly. Germany did develop radar technology, but treated it as one important area among many. It didn't receive the focused, relentless priority that Britain gave it. By the time Germany recognized how critical centimetric radar had become in 1943, the gap had grown too wide to bridge, given the limited time and resources available. Hutchinberg's career illustrated both the ironies and the tragedies of technological competition during warfare. During the war, he'd worked desperately to understand and copy British radar, examining equipment recovered from crashed aircraft, attending meetings, contributing to German efforts to close the technological distance. After the war ended, he collaborated with British scientists, including some of the people who'd developed the cavity magnetron he'd studied so intently during the fighting. British and German scientists worked together, using surplus Würzburg radars for radio astronomy. They tracked solar emissions and cosmic radio sources. The Würzburg radars built to track Allied bombers became instruments for peaceful scientific exploration, mapping radio signals from the Sun, from Jupiter, from distant galaxies far beyond imagination. Weapons technology found new purpose in fundamental research. Hutchinberg worked alongside people like R.V. Jones, the British scientific intelligence officer who'd orchestrated British understanding of German radar during the war and helped plan deception operations against German systems. Former enemies became colleagues, united by scientific curiosity that transcended the divisions of wartime. In the scientific community, wartime hostilities gave way to shared pursuit of knowledge. The captured magnetron from Rotterdam that had revealed the technological gap to German scientists in February 1943 eventually made its way back to British hands after the war's conclusion. British intelligence teams recovering German radar equipment and technical documentation found German magnetron copies and examined how well Germany had managed the reverse engineering challenge. Technical analysis demonstrated that German copies were functionally equivalent to British originals, confirming that German scientists had solved the reverse engineering problem competently. The LMS-10 magnetrons worked properly. They generated appropriate power. They operated at correct frequencies. German engineers had mastered the technology and could manufacture working copies given sufficient resources and time. What they couldn't overcome was the industrial scaling challenge required for mass production during wartime conditions when materials were scarce and Allied bombing disrupted everything. British magnetrons were being produced by the thousands each month in multiple factories. American production reached similar scales. German production peaked at perhaps 20 units monthly. The gap wasn't scientific knowledge or intellectual capability. It was industrial capacity and the strategic decisions that determined how capacity got allocated. Germany could build magnetrons. Germany couldn't build them in the quantities that would alter strategic equations. The lessons from the cavity magnetron surprise shaped thinking about technological intelligence and research management after the war in ways that influenced how military establishments approached technology during the Cold War. Both sides recognized that understanding adversary technological capabilities required much more than monitoring scientific journals or conference presentations. Practical capability often diverged sharply from theoretical knowledge available in open literature. An adversary might understand scientific principles without being able to implement them effectively. Conversely, they might achieve practical success despite apparent theoretical limitations. Assessing technological threats required understanding adversary science, but also industrial capacity, research infrastructure, how strategic priorities shaped resource allocation, and management approaches to technology development. The cavity magnetron surprise illustrated the dangers of mirror imaging, of assuming that adversary capabilities and limitations matched your own. German engineers had calculated that high-power centimetric magnetrons were impractical. They'd assumed British engineers faced the same limitations and theoretical obstacles. That assumption proved catastrophically wrong, with profound strategic consequences. British experimentalists found practical solutions that German theoreticians had declared unlikely to succeed. The magnetron experience also demonstrated the importance of experimental validation over pure theoretical analysis. German researchers had developed mathematical models predicting magnetron behavior at centimetric wavelengths. The models predicted instability and weak output. Rather than conducting extensive experimental programs to test or refine these models, German research accepted the theoretical predictions and focused on frequencies where theory predicted success. British researchers conducted extensive experimental investigations, building numerous prototypes, testing variations, and eventually finding configurations that worked despite theoretical predictions suggesting it wouldn't. This reflected different research cultures. German scientific tradition emphasized theoretical rigor and mathematical analysis. British tradition, particularly in engineering, emphasized experimental empiricism and practical demonstration. Neither approach was inherently better, but in this specific instance, the British experimental approach discovered solutions that the German theoretical approach had missed. The lesson was that theory and experiment must work together, with experimental results informing theory and theory guiding experimental work. Modern historical analysis places the cavity magnetron gap among the decisive technological developments of World War II. It ranks alongside radar itself, code-breaking capabilities, atomic weapons development, and proximity-fused munitions. Each represented not just scientific achievement, but successful translation of science into practical military capability at industrial scale. The magnetron's significance lay in enabling a category of radar applications that longer wavelength technology couldn't match effectively. Without centimetric radar, many Allied tactical and strategic advantages wouldn't have existed, or they would have been far less effective. With centimetric radar, Allied forces possessed capabilities that German forces couldn't counter effectively, because Germany lacked equivalent technology and couldn't develop effective countermeasures without understanding underlying principles through their own development efforts. The decade gap wasn't merely historical curiosity. It was strategic reality that influenced military operations throughout the war's final years, contributing to Allied victory in measurable ways across multiple theaters and operational domains. 70 years later, the Rotterdam magnetron story endures as a symbol of technological surprise, intelligence windfalls, and strategic failure in technology development. That small copper cylinder, machined with extraordinary precision from solid copper blocks, represented years of British research, investment, industrial development, and engineering refinement that Germany hadn't matched. When German scientists examined it in February 1943, they held physical proof that their understanding of technical feasibility was incomplete. They'd assumed limits that didn't exist. Their opponents had achieved successes German theory deemed impossible or impractical. The gap wasn't merely technological, a simple matter of one side having better equipment. It was epistemological, a gap in understanding what was achievable and how to organize scientific and industrial resources to achieve it. German science was excellent by any objective measure, but it had been directed toward different priorities based on different assumptions about technical feasibility and strategic importance. By the time Germany recognized the significance of centimetric radar, the technological and industrial gap had grown too large to close before the war ended, given Germany's deteriorating strategic situation. In February 1943, as Professor Leo Brandt examined that captured magnetron in the Telefunken laboratories in Berlin, he held evidence that Germany had lost a technological race they hadn't even known they were running. British engineers had been working for 3 years on technology, that German scientists had dismissed as impractical based on theoretical analysis. American industry was producing the devices by thousands monthly, while German industry struggled to build dozens. The path from laboratory curiosity to decisive military advantage had been followed successfully by the Allies, while Germany pursued other priorities based on different assessments of technical feasibility and strategic importance. By the time Germany recognized centimetric radar's significance and attempted to close the gap, the technological distance was too large to overcome before the war's conclusion. The captured device was more than an intelligence windfall, providing insight into enemy capabilities. It was revelation of strategic failure in technology development, a failure no amount of desperate effort could reverse, given time and resource constraints. Germany's excellent scientists and engineers could understand the technology. They couldn't replicate the years of development work and industrial scaling that had occurred while Germany focused elsewhere. The cavity magnetron story demonstrates that technological advantage in warfare comes not merely from having capable scientists, but from sustained institutional commitment to translating scientific knowledge into practical capability at industrial scale. Germany had the scientists and theoretical knowledge. What Germany lacked was years of continuous development focused specifically on this technology. The industrial infrastructure, tailored to electronics manufacturing at scale, and the strategic patience to pursue research that didn't promise immediate tactical advantage. Britain and America had made different choices, investing in radar development as a long-term strategic priority beginning in the mid-1930s when the technology was immature and unproven. They committed resources, they built infrastructure, they trained specialists, they persisted through failures and setbacks. By 1943, those investments had created advantages in the most strategically significant electronic warfare technology that Germany simply couldn't overcome. The decade gap wasn't accident or bad luck. It was the predictable outcome of different institutional decisions about how to mobilize science and industry for warfare, decisions made years before the war began. Today, microwave ovens in millions of kitchens worldwide use cavity magnetron descendants, generating microwaves at power levels and frequencies that German scientists in 1943 believed impossible to achieve, practically for military applications. The technology that decided electronic warfare battles in World War II has become a mundane consumer appliance component, mass-produced in factories across Asia, costing mere dollars per unit. The physics that seemed so challenging that Germany abandoned serious pursuit has become undergraduate engineering curriculum, taught to students who learn in hours what took years to discover during wartime research. What appeared as extraordinary achievement in 1940, requiring cutting-edge physics and engineering, became routine industrial practice within decades as manufacturing techniques improved and economies of scale reduced costs. But in the specific historical context of World War II, that achievement represented crucial advantage that influenced strategic outcomes across multiple theaters of war. The small copper cylinder captured near Rotterdam in February 1943 was evidence that warfare had entered a new technological domain where theoretical understanding alone was insufficient for competitive advantage. Industrial capacity to manufacture advanced electronics at scale would be as important as armies in the field. Germany had fallen behind in ways that couldn't be rectified before war's conclusion. Despite having excellent scientists and engineers who understood the principles once they examined the captured technology, the gap was real. When German scientists examined a British cavity magnetron and admitted with professional integrity, transcending wartime propaganda, that they were years behind in technology that would help decide the war's outcome, they were confronting the decade gap in radar physics. That gap reflected not intellectual inferiority, but strategic choices about research priorities, resource allocation, and technology development approaches made years earlier when consequences weren't yet apparent, but would prove decisive when war came.